Okay, good morning. Today is Monday, May 3rd. So I just want to make one quick announcement, which is the second chapter objective is now due May 9th. I think I set it up for instead of May 2nd. So if you finished it, great. You can go ahead and keep working ahead on to chapter 3. If you haven't, you got a little bit more time to finish it up. So let me talk a little bit more about ionic substances today. And that will pretty much wrap up chapter 2. And then next week we'll get into chapter 3. So let's talk about these ionic substances. Or compounds, right? So the first thing to say is, remember, we have this situation where the elements in the first column, in column 1A, they tend to form ions with a +1 charge. And then in the second column, they tend to form ions with a +2 charge. And then all the way over or almost all the way over to the other side of the periodic table, you have group 7A. And so that includes fluorine, chlorine, bromine, and iodine. They tend to form -1 ions, which are called anions, right? A negatively charged ion is an anion. 6A, oxygen, sulfur, selenium, tellurium. 5A is nitrogen, phosphorus, arsenic. And you can go a little bit further than that. Sometimes people, you may see this, you may see that 4A, they put carbon and silicon. And the order would be -1, -2, -3, -4. And this would be +1 and +2. But there's this whole periodic table in the middle, the transition metals. And we don't have any real specific pattern for them. So it's not as obvious. So what we do is we have the system. And the system is that if it's a transition metal, what we do is we name it. So for example, copper is a transition metal. So copper is element number 29. Cu, has an atomic mass of 63.55. Okay, so it's element number 29, right? So what you do is you name it. You name the element copper, and then you indicate what the charge is using a Roman numeral. So the name of the compound would be something like copper 1 oxide. We would pronounce that copper 1 oxide. If, on the other hand, it has a charge of +2, then you put Roman numeral 2. And these would be two different compounds. The one on the top, the copper is +1. So in traditional, remember what you do? You write plus as a superscript. You write a 2+ as a superscript. So when you see these Roman numerals, those are there to indicate what the charge is. It's called the Stock system, okay? And that's used with the transition metals for the most part. So we generally don't use those, for the main group elements because we know what their charges are. We only really, generally, we use it for the transition metals. So let me show you an example here. Saved photos. Let's try a new one here. So suppose I said, hey, what is the formula for copper 1 oxide? Okay, what you would do is you grab your periodic table. You're not going to do this without the periodic table. Grab it, look up copper. Okay, you say, oh, copper is Cu. And then you look at the Roman numeral that's next to it. That's a 1. So that right there tells you the charge is +1. Okay. Now you say, well, what's oxide? Oh, I know what oxide is. Oxide is oxygen, right? And that's in group 6A. The charge of any ion in group 6A is -2. So you now have O2-. Okay. Now comes the part where we draw the formula. What is the formula, chemical formula for copper 1 oxide? The rule or the idea, the concept you got to get here is that you have to have the same number of ions such that the charges are equal to each other. So what I mean by that is if you have +2, you got to have -2. You can't have +2 and -1. That's not a compound, okay? So to get a compound, the positive charge has to equal to the negative charge. But you cannot change these charges here. Those exist in nature. They're immutable. So we cannot say that copper-1 oxide, the copper has a charge of +2. It just has whatever it has, okay? So what do you do then? What you do is you combine them so that the charges cancel. So here's your logic. This one, even though we don't write a plus, even though we don't write a 1, it's +1. This one is -2. So you need 2 of the +1s to counter the -2. We're not going to put in a half of a -2. So we're going to have 2 of the +1s, right? So really the trick here is just to figure out how many of the copper ones you need in order to balance the charge with the oxide. The answer is 2. You need 2 positive ones. So how do we write that? A chemical formula doesn't show charges. It's improper to show the charge in a chemical formula unless it's an ion. These are ionic compounds, so they're not going to show the charges. So what you do is you just write the number of ions as a subscript. Okay, so this means that we have 2 copper 1s and 1 oxide, right? Again, we don't write a 1 here. It's improper notation to write a 1, just as it would be improper notation to write a 1 here. We don't write a number if it's 1, so it's copper plus. So this right here, be careful. You're going to have a tendency. People naturally will say, oh, this is copper 2 oxide because there's 2 coppers. But that's the opposite of the meaning there. If you say that's copper 2 oxide, you're getting the wrong interpretation of what's happening. The 2 is how many there are. The charge is given by that number right there. So the reason this is a 2 is because we need 2 of the positive ones. Let's try another one. So let's say I say, hey, I've got iron 3, and let's do chloride. Okay, so what you do is you pull out your periodic table, you look up iron. Iron is ferrum, it's Fe. There's your charge. You look up chloride. Chloride is in group 7A. Okay, group 7A is -1, right? So that means it's Cl minus. Okay, and then you say, okay, how many chlorides do I need to balance this +3 charge? You need 3 of them, right? 3 negatives will balance +3. So that means you need 3 of them. So the way you write that is Cl3, right? You need 3 of the -1s to equal -3. The -3 has to counter the +3. So you're going to write that as a subscript, right? So the subscript is the number of the ions. And you know, if you want a picture of what this looks like, it looks like this. You've got an iron with a charge of +3, and then you've got 3 chloride ions attached to it, right? So each one is -1. There's 3 of them. There's only 1 iron because the iron is +3. But what if it's a different form of iron? There are different forms of these transition metals. That's how they differ. I could say, hey, there's a compound called iron 2 chloride. So it's almost the same problem. The difference is the charge is +2. So now you have Fe2 plus, Cl minus, right? Again, chloride is in group 7A. The anions are changed from -ine to -ide. So chlorine becomes chloride, bromine becomes bromide, iodine becomes iodide. So, okay, you got +2. So how many of these negatives do we need? We need 2 of them to balance that charge. So that means we're going to have FeCl2. The number of the ions is right there. Again, a picture. Here's your iron 2. Here's your chlorides. It takes 2 chlorides to balance that +2 charge. So that's why the positions in the table are important. Minus 1 if you're in group 7A, right? Minus true if you're in group 6A. Minus 3 if you're in group 5A. Okay. And, but the transition metals, which are here in the center, they could be +1, they could be +2, 3, 4, 5, 6, 7. There's a couple of exceptions to that, to the transition metals. So we'll call these exceptions. Just memorize the exceptions. The first one is zinc. Zinc is element number 30. It's always +2. The next one is silver. So silver is 47. It's always +1. Okay. And then over here in group 3A, so group 3A, there's an exception there too, which is aluminum, which is group 13. I'm sorry, it's element number 13, is +3. Or yeah, +3. Okay. So those are the three you can memorize. There's aluminum, which is 13, which is +3. There's zinc, which is 30, that's +2. And there's silver, which is 47, and that's plus. And there's actually a pattern there, right? AZA, you can remember it that way, AZA, +1, +2, +3. It's kind of cool in the periodic table there. So those are the three metals that you actually know what to charge. So in general, you won't see zinc 2 chloride because it's understood, oh, zinc is always +2. You won't see silver 1 chloride. You might see it. Sometimes people will still put it, but silver's got to be +1. So it's just going to be called silver chloride. And the same with aluminum. Aluminum is aluminum chloride, not aluminum 3 chloride generally. Okay. So those are the three metals that you know. But all the other transition metals in here, those ones, you don't know what their charges are unless someone tells you what they are. So they're going to say, hey, it's iron 2. But you might have to go backwards too. Keep in mind that, right? So let me take a look at an Aleks problem, just so you can see how this works in terms of Aleks, okay? So this is called deducing the empirical formula of a binary. We're only going to deal with binary compounds, a binary ionic compound from its name. Okay, kind of cool. So let me come back over here. So what they do is they say, okay, we're going to give you the name. It's called copper 1 bromide. You have to get the empirical formula. We'll talk more about empirical formulas when we get to chapter 3. Cesium bromide, I'm sorry, cesium iodide. And you're going to do the empirical formula for that one too. Okay, so for these two, you're going to notice there's a difference between the two, right? The first one has the Roman numeral, the second one doesn't. So let's go through each one. Okay, copper 1. What are they telling us when they say copper 1? Copper 1 is a transition metal, element number 29. Okay, so we don't know what the charge is. It's a transition metal. The transition metals go all the way from 21, which is scandium, to 29, which is copper. And then the next one over was that zinc, right? Number 30 is zinc. Okay. So the transition metals, depending on who you speak to, are all the elements from 21 to 30 or all the elements from 21 to 29. Some people will debate whether zinc is really a transition metal. It's always +2, so it doesn't transition, right? Whereas 21 through 29, they all have different states. They can all be +1 or +2 or +3, depending on which one you're talking about. Okay, so this one's copper 1's transition metals. So they told us the charge. So we know it's copper 1, so copper plus. Then you look at bromide. Where's bromide? Well, bromide is actually, it's in the same row as copper. It's number 35. And it's group 7A, right? So 7A minus 1. So we know it's Br minus. Okay. So now you say, okay, well, how many positive charges do we have? 1. How many negative charges do we have? 1. They're equal. If they're equal to each other, you can just write the formula. You don't need to have 2 or 3 of them, right? The positive balances the negative. So you just write it as Cu. Write the metal first and then the non-metal. So for ionic compounds, you write the metal first and then the non-metal second. And there you go. There's your chemical formula. Okay. So copper 1 bromide is CuBr. Now, what about cesium iodide? Cesium. Okay, well, where's cesium? Cesium is actually in group 1A. Okay, it's element number, I think it's element number 55. Barium is 56, so it's 55. Okay, group 1A plus 1. Okay, iodide. Iodide is right underneath bromide, right? So its iodide is 53. So group 7A minus 1. So what do we have? We have CS, which is plus 1. Remember, you don't put the 1. And then you have I, which is minus 1. Again, just like the previous one, they're equal to each other. Plus and minus, right? They're not plus 2 and minus 1. They're plus 1 and minus 1. So that means you can just write it as CS. Oops, sorry. Get these symbols confused. CSI. College of Staten Island, right? Okay, so notice those two, even though one's a transition metal and the other one is a main group element, which is cesium, group 1A, they're going to have very similar formulas, right? And the reason they have the same formula, essentially, is that they're both plus 1 ions, right? The metal is plus 1 and the non-metal is minus 1. So it's going to be just 1-to-1 ratio. And that's called the empirical formula. Let me show you another example. Let's see, let me come over here to Alex. Let's do another one, show another one. Okay, well, I'm going to find one that's a little trickier if I can. Okay, good. This one's a little better. This one's a little trickier. So we're going to give you the name, which is calcium fluoride. Okay, and again, you want to write the empirical formula. And then we've got chromium 2 iodide. Again, when you see that Roman numeral, that tells you right there it's a transition metal. It's going to be one of those elements in the middle of the table. If you don't see a transition metal, if you don't see a Roman numeral, then that's going to be one of the main group elements. It's going to be group 1A, group 2A, or it could be zinc, silver, or aluminum, right? Aluminum, zinc, AZA, aluminum, zinc, and silver. Those are the 3 metals that you don't have charges for. Okay, so let's go through it. Calcium, you're just going to look it up in the periodic table. You're going to find that calcium is in group 2A. Okay, it's element number 20. Group 2A is plus 2, right? So that tells us right there, we know it's calcium plus 2. I say plus 2, but you really want to write it 2 plus. And then we got fluoride. Where is fluoride? Fluoride is all the way in group 7A. What is group 7A? Minus 1. So now we have F minus. So this is calcium fluoride. Okay. So how do we deal with calcium fluoride? Well, you got plus 2 and minus 1. How many of the negatives do you need to get 2? You need 2 of them, right? 2 negatives will give you negative 2. So that means we need 1 calcium and 2 fluorides, right? 2 times negative 1 is negative 2. There's only one of these, right? 1 times plus 2 is plus 2. So the negative and the positive are going to cancel each other. That's what you're looking for. That's what ionic compounds do. So for this compound, you got your calcium, which is 2, and then you got your fluoride, which is minus 1. So there's going to be 2 negatives to balance that 1 positive 2. Chromium. Now you see the Roman numeral, chromium 2 iodide, right? So if you got a Roman numeral, look in the middle of the periodic table. Okay, and what you're going to find is that chromium is element 24 Cr. It's an interesting element. Chromium can have many different charges. It could be +2, it could be +3, it could be +6. It has different charges it can exist as. This is chromium 2. So since they gave us the Roman numeral, we know the charge. And then you got iodide. Iodide is in group 7A. It's actually right, it's in the same column as fluorine, so it's -1. Okay. So chromium 2 iodide, how many of the negatives do you need here? It looks like you need 2 of them, right? 2 of these negatives will give you -2, which will balance the charge. So you need 2 of the negatives. So we write it as CrI2. Okay. There you go. So main group elements are these ones like calcium and lithium and sodium. And then the transition metals are the ones in the middle, elements 21 through 30. And those are the ones that are going to have the Roman numerals. Okay. Remember, when you're writing a chemical formula, you want to do the metal first and then the non-metal. We generally don't want to write it this way. That would be considered poor form. Okay. Cation, anion, positive, negative. Okay. Okay, let's talk about the polyatomic ions. The polyatomic ions are cool. There are a bunch of polyatomic ions in nature. For those of you that are in biology or medical field, the ones that are really important for you are this is a phosphate, hydrogen phosphate, carbonate, hydrogen carbonate. If you're a chemistry major, then there's other ones that are important like nitrate, but hydroxide is important, hydronium is important. So let me make a little list here of the polyatomic ions. Polyatomic ions are really, they're associated with minerals and they're associated with water. Polyatomic ions are often dissolved in water. And they are also locked into essentially rocks as minerals. And we mine them and use them for industrial purposes and commercial products. Okay, so let's go through the polyatomic ions. First of all, polyatomic ion, just what that means. Poly means several or many. Atomic means atoms, so several or many atoms. And these are ions, which mean that they're positively charged or negatively charged. Okay, so let's go through a bunch of them. So here are the 2 that I think are kind of, in a way, the most important ones if you're learning chemistry. Hydronium and hydroxide. Okay, hydronium and hydroxide. Now, I'm going to make 2 columns. The first one is cation, and the second one is anion. Remember, cat is positive, an is negative. So anions are negative. The first one is hydronium. It's H3O plus, it's a cation. It's essentially a water molecule with an H plus attached to it. So that's a 3, right? I'm looking on the screen, it almost looks like a 2, but that's a 3. So H3O plus is called hydronium. If it ends in IUM, it's positive. If it ends in IDE, ide, it's negative. So hydroxide, right there, you know it's negative. It's got to be an anion, right? Because it ends in IDE. So hydroxide is OH minus. And those 2 ions are related to each other, right? If you think about it, what is the difference? They both have 1 oxygen. They both have hydrogens. One only has 1 hydrogen, the other one has 3, right? So if you were to add 2 hydrogen ions to the hydroxide, you'd have a hydronium. Or if you were to take 2 hydrogen ions off of the hydronium, you'd have a hydroxide. Okay, so those are the first 2 you should know. And then there's a bunch of others. So let's go through them. There's carbonate. Carbonate. Now, what about 8? What if it ends in 8? Okay. If it ends in 8, it's also an anion. So it's over here on the right. So carbonate has carbon. There are 3 oxygens, and it has a charge of -2. Okay. Cool polyatomic ion. Carbonate is related to carbon dioxide. If carbon dioxide is bubbled into water, it reacts with the water to form carbonic acid, and then that carbonic acid will dissolve to form carbonate. Generally it forms bicarbonate. So let me show you what the next one is. This is called hydrogen carbonate. Most people call it bicarbonate. Bi means it has a hydrogen. So hydrogen carbonate or bicarbonate is HCO3 minus. Okay, also an anion. Okay. These behave just like ions, just like chloride or bromide or iodide. Notice you're going to be a lot more anions than cations. They're just in nature, there seem to be many more anions than there are cations. Most of the cations in nature are monatomic ions like sodium, potassium, whereas the anions having to do with oxygen is negative typically. Oxygen just forms all kinds of ions, and they tend to be negative because oxygen tends to be negative. Okay, so there's hydrogen carbonate. So there's carbonate, hydrogen carbonate, or bicarbonate. There's also phosphate. Okay, phosphate, again, ATE, right? If it ends in ATE, it's negative. So PO4, for those of you that are biology majors, that's an important ion, right? That's involved in hydrolysis and condensation involving ADP, AMP, ATP, all of those energy molecules in biology. Okay, so there's phosphate. Well, guess what? There's also a hydrogen phosphate, just like there's a hydrogen carbonate. It's HPO4 -2. So every time you add a hydrogen, you lose a negative charge. You become a little bit less negative by 1. Okay. You can also have 2 hydrogens, dihydrogen phosphate. So that would have 2 hydrogens and it would be -1. Two hydrogens. Okay. Now, there are also nitrogens. So nitrate, again, ends in ATE, so we're going to put it on the right column, right? So what's nitrate? Nitrogen. This one has 3 oxygens and it's -1. Okay. So 8s are negatives, they're anions. Notice there's no real pattern in terms of the number of oxygens. For example, phosphate has 4 oxygens and a charge of -3. Nitrate has 3 oxygens and a charge of -1. Some of these things you just need to memorize. Okay, so those are some of the 8s. Let's see, carbonate, nitrate, there's chlorate. What do you think chlorate is? Well, it's Cl, right? Chlorine, chlor, right? And then it's got oxygens, -1. Okay. You sometimes will see per. What does that mean? Is it's got a per. Per generally means extra oxygens. Okay. So you may see something like perchlorate. So you got 1 extra oxygen. Per means 1 more. So if 8 has 3, per 8 is going to have 4. If 8 has 2, then per 8 is going to have 3, 1 extra oxygen. So there's actually a pattern to this. I'll show you the pattern in just a moment. Okay, but there's also the second type. Well, let me do one more cation. Actually, I'll do the last cation at the end. There's a third type of ending, which are anions. So there's ide, which is an anion. There's ate, which is an anion. There's also ite. And so let me show you an example. Nitrite. Nitrite is also an anion. So if it ends in ITE, it's an anion, right? So most of these, like I said, are anions. The only ones that are cations are IUM. Is positive. Ide, ate, ite are negative. Okay, so there's nitrite. Okay, there's also, let's do chlorite. Chlorite is ClO2 negative, right? Okay, so ites are negatives. They all have oxygen, right? Notice like all these polyatomics that are on the anion side, they all have oxygen. Shows you how important oxygen is, right? It's a pretty important element. It's involved in all of this chemistry, okay? So what's the take home from this? You got cations, you got anions. The cations end in IUM, they're positive. The anions end in ide, ite, or ate. If you look at them, the vast majority of them, they have a non-metal like phosphorus, nitrogen, chlorine, carbon. Those are all non-metals with some number of oxygens, right? So non-metal with oxygens, they end in ide or ate or ite. And I'm going to do the one last one here. This is not an exhaustive list. There's many more polyatomic ions than this, but that's ammonium. And I wanted to put it last just so you could kind of see. We started with a cation. We're going to end with an anion, right? With a cation, ium. And what is ammonium? Ammonium is NH4+. So these two cations, those two you should memorize. Memorize the hydronium, H3O+, memorize the ammonium, NH4+. And then the anions that I recommend memorizing are, I'm going to put a little asterisk next to that next, or check. Hydroxide, carbonate, hydrogen carbonate, phosphate, hydrogen phosphate, dihydrogen phosphate, nitrate, chlorate, perchlorate, nitrate, and chloride. Yeah, go ahead and memorize. So there's the list right there for everything on here. Okay. If you memorize those, you're doing pretty good. Those are not the only ones. There's other ones out there, but this is a good start. And then what you can do, just make flashcards with them. And then what you can do is you can add other polyatomic ions that you come across and put those on flashcards as well. Okay. Now there's one aspect of these polyatomic ions that I want to show you, which is a pattern. And that is if you have a halogen, so these are the ones with the halogens. There's an interesting pattern. So let me show you what it is. Remember, halogens are group 7A, right? Just so you remember. Halogens are 7A. So look at these polyatomic ions, right? How do we know they're polyatomic ions? They've got more than one atom and it's charged. That makes it a polyatomic ion, okay? Now, notice they're all the same. It's all chlorine with oxygen and -1. There's a pattern to this, right? These are relatively rare, but there's 3 of them. There's the ones with chlorine, the ones with bromine, and the ones with iodine. There you go. There's 3 of them. Those are the halogens, right? Chlorine, bromine, iodine, group 7A. Now be careful, because what we used to say, oh, you know, it's a halogen, group 7A -1, but that's only if it's a monatomic ion, right? If it's Cl minus, that's -1. But here it's part of a polyatomic ion, so it's a different analysis. So here's the pattern. We want these groups to kind of have the same name, but be different, right? Kind of like, you know, if you have people in your family, you might have the same last name, but different first names. And you might even say, hey, let's be clever about it. We have a lot of kids, so let's all have them start the first letter of their first name will be the same. Like Amanda and Annie, and so same idea. So here's what you get. If it's one of these three groups, and you can recognize it, halogen with oxygen negative. Here's what you do. The first one in the series is hypo, and then it's chlorite. Okay, so the first one's going to be hypo. I don't want to use a little dash because the dash you might think is a negative charge. Okay, so it's hypo. The last one starts with per. Okay, so hypo and per. Per is really shorthand for hyper, right? Hyper or per. Okay, and then the first two end in ite. So hypochlorite. The second one, you just drop the hypo and it's just chlorite. Okay, so that's cool. Hypochlorite and then chlorite. And then the next two, it ends in ate. And then perchlorate. So notice the pattern. First one's hypo, last one's per. The per is more oxygens. It's like hyper, it's got lots of oxygens, right? The first two end in ite, the last two end in ate. So ite. So ate always has more oxygens than ite. Ite always has fewer oxygens than ate. So it's hypo, ite, then ate, then per. It's like conjugating verbs, right? Okay. And so same thing here. Hypo, bromide, right? The first ones are ite, and then just bromite. And then bromate. And then perbromate. Okay. Same thing with the iodine. Hypoiodite, iodite, iodate, periodate. Right? So first one's hypo, last one's per. First two are ite, last two are ate. The middle ones, no prefix, no hyper, no hypo or per. And there you go. So those are the three groups that you will sometimes see in some of these problems. And you might say, well, why does that say per? The reason it says per is because there's possibility of up to 4 different ones. Most of the ions, most of the polyatomic ions don't have that potential. They can't make 4 different types. Most of them can only make 2. Okay. So if they can only make 2, we don't need the hypo and the per. We just need the middle 2. So for example, going back to the previous list, this one was nitrite, right? If there's only 2 possibilities, you don't need the per and the hypo. So then it's nitrite, right? NO2 minus is nitrite. Remember, more oxygens is 8, fewer oxygens is ite. And there you go. Okay. But again, remember that what you're looking at are a non-metal combined with oxygen. The vast majority of polyatomic ions, those are the ones that we deal with. There are others out there though. So there are some where it's, no oxygen in there, and you'll see them out there, but those are the vast majority ones. So let me show you an example here. Okay. Oh. All right, good. Merci, Nodi. Okay. Let's take a look at this one. So in this one, this is called identifying common polyatomic ions. Okay, so you're going to complete a little table. So the first one is they say ammonium cation. Now that's actually kind of nice. They actually call it a cation. That's telling you it's positive. And then you're going to write the formula. And then they may actually give you the polyatomic ion, the formula, sorry, and then have you identify which one this is. Okay, so there's one in here that I didn't give you, but we'll go over that one separately. Okay. All right, relatively simple. What do? You just, go from your little table, make yourself a little table of these things. Ammonium, we looked at that one. That's NH4 plus. And remember, positive is EM. ClO3 minus, that's one we just looked at, right? That was the hypochlorite, chlorite, chlorate, perchlorate, right? So the perchlorate had 4, the chlorate had 3, so chlorate. And I guess, just to be consistent with what they're saying, we'll call it an anion, chlorate anion, right? If it's negative, it's an anion, okay? What about this one, the third one? Third one, CO3, right? Not ClO3, but CO3. That's the carbonate, right? Carbon. So that's the carbonate ion. Okay, now this one's more complicated. This is one I haven't talked to you about. This is organic. It's kind of cool. Organic ions have carbon and hydrogen in them. And this is one of those. It's got carbon and hydrogen. So this is an organic compound. It's an organic polyatomic ion. And it's really, as far as I'm concerned, it's the only organic one we really need to know in general chemistry, at least until you get up to the second semester of general chemistry. So if you see this one, it can be written in different ways. So you may see it written this way. So instead of writing CO2 minus, they write COO minus. It can be written that way. This is called the acetate ion. Oops, sorry, anion. Okay, so there you go. So that's the acetate anion, okay? And there you go. Let's see, take a look and see if there's one more. I just kind of want to go through there to see if there's any in here. Okay. So if you look in your ebook, in chapter 2, there's a table of the polyatomic ions. And you can certainly look at all of the table of the polyatomic ions, and that will give you an exhaustive list of these things. Okay, so there you go. So now let's try to figure out, just like we did with the monatomic ions, let's try to do formulas with polyatomic ions. So this is kind of interesting. So this one is predicting formula of ionic compounds with common polyatomic ions. So we're gonna get the formula just like we did before. What's interesting about this particular one is just formatted differently. They give you a list of all the ions. And then you just got to write them all down there, okay? Oh, they say at least 4. So at least 4. Okay, well, if you're taking a test and you see this problem, you might want to stop at 4, right? Because if you do more than 4, it takes more time. But let's take a look here. So here's the logic that I would use. What I would do is I would first identify the cations. So I'm going to separate them into cations and anions so that you can see what the possibilities are. So this one's positive. This one's positive. Okay, those are the cations. And then you get the anions, right? The anions, I'll put 2 lines under those. OH minus and BrO3 minus. Okay, the reason that it's useful to do that is because an ionic compound has a cation and an anion. More than one, right? It could have more than one. There could be 1 or 2 or 3 or 4 or whatever, but it's a combination of cations and anions. It's not a combination of cations with cations. It's not a combination of anions with anions. It's positive, negative is attractive. Positive, positive is repulsive. Negative, negative is repulsive. So they both have to be opposite charges to form an ionic compound. So what that means is your iron is going to combine with hydroxide and bromate, but it cannot form anything with lead. Same thing, the lead can go with the hydroxide and the lead can go with the bromate, but it can't go with the iron, okay? Same thing, hydroxide can't go with bromate. So let's do the iron one first. So iron is +2. Hydroxide is -1. So to get -2, you got to have 2 hydroxides. So FeOH2, 2 hydroxides. But here, this is confusing. This is actually misleading. When you have a polyatomic ion, if you have more than one of them, you got to put parentheses around the polyatomic ion. Why? You would, maybe someone reading that would say it's Fe, 1 iron, O, 1 oxygen, H2, 2 hydrogens, but that's not what we mean. We mean that we have 2 of the hydroxides because we have to have 2 negatives, right? Remember, we're balancing the charge. So 2 negatives balances the positive 2. So make sure you put parentheses. If you have more than 1 polyatomic ion, put parentheses around the polyatomic ion and then put the number after the parentheses. So same thing, iron and bromate. Okay, remember, hypobromate, hypobromite, bromite, bromate, perbromate. So this is bromate, okay? Bromate is also -1, just like hydroxide. So that means you need 2 of the bromates. So you write it as Fe, BrO3, but you got to put the parentheses to indicate that there's 2 of the bromates, okay? No charges. We don't write charges in the chemical formula. The charges are written for the ions, but not for the chemical formulas, okay? Now, what about the lead? The lead, same thing. The lead is going to combine with hydroxide. That's 1 compound. The lead is going to combine with the bromate. That's the 2nd compound. So let's figure out how to do the lead. So lead is +4. Hydroxide is -1. So that means we need 4 of the hydroxides, right? 4 negatives. So Pb, it's polyatomic ion. If there's more than 1 polyatomic ion, you write parentheses, and then you put the number after there. You need 4 of the hydroxides to balance the +4. And then you got the lead with the bromate. Same thing. Bromate is also -1. So you're going to need 4 of them, right? To balance that +4. 4 -1s is going to balance +4, right? These have to be opposite. The whole idea here is that the anion has the negative charge and the cation has the positive charge. So you got to have the same number of anions. You have to have the number of anions so that their charges add up to the same as the positive charge. Be like, I need 4 quarters to equal $1. So if I have $1 in paper, how many dimes do you need to equal that? You need 10 dimes, right? So you'd write it, as $1 dimes 10. Okay, so same thing here. You got 4 of the negatives to equal the +4. And that's all hidden in the chart, in the formula. The formula doesn't show that to you. So it's sort of implicit. Okay, I want to make sure that I do one more type of polyatomic ion. And then I'll just do a brief mention of the molecular compounds. So this one says naming ionic compounds with common polyatomic ions. Okay, so now we're just going to name them. So in the previous one, we were writing the formulas. Now we're going to add one more thing. So for this one, what they're going to do is they're going to give you each ion that you're combining. So here's your cation. Here's your anion. And then they want the empirical formula And then they want you to name it. What's the name of the formula? What's the name of the compound, right? So let's take a look at this one. This runs you through the whole kind of thing. The first one here is easy because they made the charges equal, right? If the charges are equal, it's just 1 to 1, right? You don't need to have more than one of them. So the empirical formula is, since this is +1 and I shouldn't do that. If this is +1 and this is -1, you just need to combine them 1 to 1. So you just write NaClO. Okay? Cation first, the metal. Anion second, the nonmetal. Metal, nonmetal, or cation, anion. Okay? Now, how do you name it? Relatively simple. Same kind of system as we were using before. You name the metal, the cation. Just use the element's name. You just look it up on the periodic table. Just call it sodium. Then you just name the polyatomic ion. So sodium, what's ClO minus? Well, you have to go back to your little flashcard, right? Remember, it was ClO minus, ClO2 minus, ClO3 minus, ClO4 minus. It was hypochlorite, chlorite, chlorate, perchlorate. So the first one where you only had one oxygen was hypochlorite. So sodium hypochlorite. So it's going to be two words. The first word is sodium. The second word is hypochlorite. Okay. Let's try another one. They give you this ion and they give you this ion. Okay. First, they want you to write the empirical formula. Okay. Well, this one's +1. This one's -1. They're equal again, right? If the charges are equal, you just combine them 1 to 1. So you write the cation first and then the anion. No charges written. Okay. The formula doesn't have the charges. So now you say, okay, we name the metal first, sodium. Okay, just look it up in the periodic table. What's the name of the element? It's called sodium. You don't call it sodium ion. You don't call it sodium cation. In the chemical formula for a compound, you just name the element. The polyatomic ion, what's that one? Well, that was, again, in that same series. ClO minus was hypochlorite. ClO2 minus was chlorite. So this one's called chlorite. Okay, name the element, the metal, the cation, if you want to call it that, and then name the polyatomic ion. And then the last ones here is Na plus and C2H3O2 minus. Okay. Now, I'll be honest with you, every time you look at these problems, they're going to write acetate differently. I don't know why they do that. They're not consistent. I guess they just want you to know. Acetate, that ion can be written in different ways. It can be written as CH3CO2 minus. It can be written as CH3COO minus. And it can be written this way. So acetate is that ion we talked about earlier. It's written in 3 different ways. That's just the reality of how chemists operate. Sometimes it may seem that chemists are just trying to confuse people, and to be honest with you, it's probably true. Okay, so let's take a look here. We've got the Na, so we name the metal, sodium. Oh, I'm sorry, we're going to do the empirical formula first. Okay, so let's do the empirical formula. First, you look at the charges. This one's +1, this one's -1. If they're equal, you just write them out. Na, C2H3O2. Okay. Name the metal, sodium. Name the polyatomic ion, acetate. Okay, sodium acetate. Okay, let me see if there's another one here. For the most part, they're giving you easy ones. They don't give you particularly hard ones. So let me show you one more then. Okay, so for this one, they give you Fe3+, and then they give you PO4 3-. Okay, so again, the idea here is what's the empirical formula? And then what's the name of the compound? Okay. All right. So how do we deal with this? You got Fe3 plus, right? So that's iron 3. Over here, you've got PO4 minus 3. That's phosphate, right? Okay. So the empirical formula. Again, they're giving you mostly ones where the charges are equal to each other, right? Those have the same charge. If they have the same charge, you don't have to have 2 or 3 of them. You just write FePO4. Again, cation, anion. Then what you do is you say, okay, how do we name it? The only thing that's different here is that that's a transition metal. And remember, with the transition metals, you have to tell people what the charge is with Roman numerals. Okay, we talked about that earlier today. Iron 3. Okay, so this is going to be called iron 3. And then you just name the polyatomic ion. 2 words. Make sure you put a space in between there, right? So iron 3 phosphate would be the name of that one. So transition metals, you have to have the charge written over there, okay? Now let me show you one where they're not exactly the same charge. So there's only one in here. So I'm going to show you that one. Okay. So see how it's calcium and it's +2? But calcium is in group 2A, so you don't need the Roman numerals. The Roman numerals are only used for the transition metals, okay? So what's the charge, though? +2. What's the charge here? -1. So that means we need more than one of the anions, right? You need more than one of these to balance the +2. You need 2 of them, right? So how do we do that? You write the chemical formula for the metal, and then you got to use parentheses for the nonmetal, okay? So see the parentheses there? That's telling us that we need 2 of them. Why do we need 2? Because if you've got +2, you need -2, but you can't change this number. You just change how many you have. It's going to be essentially calcium with 2 of these anions. Okay, now this is not one of the anions that I showed you earlier. This is called permanganate. It's actually a pretty important anion in chemistry. It's used in all sorts of reactions. So just look it up in your table, and it's called permanganate. Okay, so now we name it. Calcium. We don't need the Roman numerals again because it's group 2A. It's not a transition metal. And then you name the polyatomic ion. Did I spell it right? Permanganate. Calcium permanganate. Okay, and there you go. That's pretty much how it works. Let's see. I'm going to take just a couple minutes here to talk a little bit about what are called molecular compounds. So molecular compounds are combinations of nonmetals. Okay, so for example, Cl2O7. See how there's only chlorine and oxygen? Chlorine is in group 7A, that's a nonmetal. Oxygen is in group 6A, that's a nonmetal. No charges. These are not ionic compounds. They are not made up of ions. So ionic compounds are made up of ions. Molecular compounds are not, and they involve nonmetals. Here's another example. N2O4, right? This is in group 5A, this is in group 6A. 2 nonmetals. Those are called molecular compounds, not involving ions. They're kind of cool. Essentially what happens is the atoms are bonded to each other through what you might call molecular bonding. We actually call it covalent bonding. And it takes a little bit of experience to figure out what the structures are, but you'll learn that in the next course, toward the end of the course. So N2O4, for example, has 2 nitrogens in the middle, And then there's 2 oxygens attached to each of the nitrogens. These are not ions. They're not negatively charged. They're not positively charged. So they're really cool. They're cool substances, and they're important in all sorts of things. So nonmetals with nonmetals, okay? Here's what we do with them. We name them. We name the first element, and then we name the second element. But we name the second element changing the ending to IDE, so IDE. So for example, here's an example, right? This one's in group 5A, so that's a nonmetal. This one's in group 6A, that's a nonmetal. So you name the first element, nitrogen. Okay, that's easy enough. And then you name the second element, but you end it in IDE, so oxygen. I'm sorry, oxide. Okay, now, in order to take into account you can have more than one nitrogen and more than one oxygen, we use what are called prefixes. And there's just a set of rules with using these prefixes. So let me show you the prefixes. If you have one atom, so this is the number of atoms for that element, it's mono. If you have 2, it's di. 3 is tri. 4 is tetra. 5 is penta. 6 is hexa. 7 is hepta. 8 is octa. 9 is nona. And 10, I'll write that over here, is deca. Okay? So those are called the prefixes. So the prefixes are used always with the second element. So the second element always has a prefix to it. The first one always has a prefix unless there's only one. So for example, see how there's only one nitrogen? We wouldn't say mono nitrogen, we just say nitrogen. But the second element always has one. So how do we deal with that? NO. Well, first one, if it's a 1, we don't use a prefix, but the second one we do. So it's going to be mono. But we never put O and O together. Avoid monoxide. It just sounds weird. So you just say monoxide. Okay. So if you have 2 O's together, you draw, and that oxygen is very common. So that's going to happen. If you just have, if the name of the second element starts with an O, you don't want to put the mono, you just put monoxide. Okay. So let's go through these here. I'll show you how to do these ones here. Okay, when do we use this system? When you got 2 nonmetals. Right side of the periodic table. Okay, so here we go. We got chlorine. So what you do, this is how I do it. I say, oh, I got chlorine. So you name the first element, leave some space. You name the second one, but you end it in IDE, so oxide. Then the first element, if it's only 1, you don't use mono. But if it's 2 to 10, you use the prefix. So how many chlorines are there? 2. So di. So dichlorine. Okay. Second element, always use a prefix. How many are there? 7. Hepta. So you write hepta. Okay, so heptaoxide. Now, some people will say if you've got 2 vowels together, you get rid of the first vowel. So some people might call this heptoxide. Okay. If it's 2 O's, you definitely get rid of one of the O's. But if it's an A and an O, it's optional. Most people will drop the A. Some people will not. Okay, let's try the second one here. First element, there's 2, so you do use the prefix. So di, nitrogen. Second element, oxide, how many are there? 4, tetra. So again, your choice, you could either write tetraoxide, but it actually sounds a little bit better to just call it tetroxide. Oops, I forgot the R. Don't drop the R. You're just dropping a vowel. Okay, so let me show you one from Aleks. Okay. Oops, sorry, delete. Okay, so let's try this. We got P4S3, NF3, N2F4, P4S7, and NH3. Ooh, this is a trick one here. That's a trick one. They're giving you a trick here. I'm going to write H2O underneath it too. There's two tricks that you got to be careful with. Okay, so let's try this. First, you identify what group they're in. This one's in group 5A. This one's in group 6A. So you know they're both nonmetals. There's no metals in here. So you're going to use the molecular system. So that first element, as long as it's 2 to 10, as long as there's not just one, you definitely use the prefix. Second element, you always use the prefix. So you look up your prefixes, 4 and 3, right? 4 and 3. Tetra, tri, right? 4 and 3. This element, you just name it, phosphorus. Tri, second element is sulfur, ended as IDE. You change the ending to IDE. So sulfide. You don't add the IDE, so it's not sulfuride. You lose the last consonant, and then you add the IDE, right? So sulfur becomes sulfide. Okay. Second one. This is when you only have one atom of the first element, you don't use the prefix. So this is just nitrogen. Second element, you always use the prefix. So trifluoride. Again, fluorine becomes fluoride. Okay. 2, so di, 4 tetra. So di, it's nitrogen, so dinitrogen. Tetrafluoride, right? So fluorine becomes fluoride. Second element, you change the IDE. Okay, here we have 4 and 7, so that's easy. 4 is tetra, phosphorus, right? You don't have to change the ending of the first element, you change the ending of the second element. So sulfur becomes sulfide, but you got 7 of them. So that's hepta. Heptasulfide. This is the trick one. You might want to call that nitrogen trihydride. Don't do it. Don't fall for that trap. These two are what we call common substances. Okay. For these two, there really aren't any more than those two for the most part. I mean, there are a few, but don't worry about them. This one's called ammonia. We don't call it nitrogen trihydride. And this one is not dihydrogen monoxide. It's just called water. So there you go. Okay. And there you go. So there's your rules, right? So first element, second element, change to IDE. If the first element only has 1, don't use mono. But if it has 2 to 10, use the prefix. Second element, always use the prefix. Avoid OO. So not monooxide, just drop one of them and just make it oxide. So monoxide, okay? Optional, if you've got an A and an O, so for example, hexoxide, it's optional. You can get rid of the A and just call it hexoxide. That's actually more common. Okay, and there you go. That's it. So 2 types of compounds, the ionic and the molecular. The molecular are 2 nonmetals. The ionic either have they generally have a metal ion, and then they have either a monatomic ion or a polyatomic ion. And that is pretty much everything for chapter 2. So next week, we will get into chapter 3. We'll start talking about mass and calculations and all of that stuff. And then we'll get into that. Okay, so reminder again, the second objective is now due May 9. So if you finished it, good for you. You can work on chapter 3. If you haven't finished it, you still have a few more days to work on that. And have a great week, okay? Take care, everybody.